Hello physics students. In this video, you're going to learn that the act of using a voltmeter or ammeter in a circuit to measure either the voltage or the current actually changes the values that you're measuring. And before I jump into showing you how, I just want to explain that this is a common theme in physics, in fact, in all of science, that measuring changes what you're measuring. And sometimes it doesn't really make much of a difference, and other times it does, and you need to know exactly when the measurement significantly changes the system and when it doesn't. Let me just give you one example. Let's suppose it's a perfectly dark night outside, and I want to check to see that my car is in the driveway. So I could shine a flashlight onto the car. Now, if you were to study light in all of its detail, you would learn that light itself has momentum. And so when I shine that light onto that car, it strikes the car much the same way as if I shot a bullet at it or even another car. So that light comes in and hits the car, bounces off, and comes to my eyes. Now, if that was a lot of momentum, the light, then maybe I go to sleep, I see my car on the driveway, I wake up in the morning and it's in the neighbor's yard now because it ricocheted as a result of the collision, or recoiled, I should say. But of course that doesn't happen because the car is so massive and light has so little momentum, so we don't have to worry when we shine the light on the car that we're going to change its location from the very act of measuring its location. But if we were dealing with something with very little mass, like an electron, and we shine light, now the momentum of the light has a significant effect. And the light comes in, hits that electron, and then you determine from that light that the electron is here, and the electron's gone. And it's no longer in the location where you measured it. So you need to know how to factor that in when it comes to electrons. Well, the same thing with meters. Measuring the current changes the current. Measuring the voltage changes the voltage. So in this video, we're going to learn exactly how you can factor the exact amount that those values change. Okay? Now, before I begin, I just want to say if you ever see this in the video, don't jump ahead and copy this down because I'm actually going to erase this and put case 1A over here first so it's kind of organized nicely. But here's the idea. Non-ideal ammeters and voltmeters. So an ammeter, ideally, would have 0 ohms resistance. It would act, as I mentioned, as a high-speed toll booth on a highway where the cars can keep going, say, 55 miles an hour, the speed limit, right, if you drive the speed limit, and they don't slow down when they go through the toll booth, so they have no effect on the traffic. Same thing with an ammeter, but the problem is it's made of actual metal inside, so that does have a resistance, so really, it might be like 0.5 ohm. Of course, it'll depend on the meter and the manufacturer, but there will be some non-zero resistance in the meter. Let's just suppose, for analysis, it's half of an ohm. And the voltmeter, ideally, when you put the probes on, you're hoping that the resistance of the voltmeter is infinity, but it's not. In real, as the real resistance might be somewhere around 10. This is mega, meaning million. So 10 times 10 to the 6th, 6 zeros after the 10, that many ohms, 10 million ohms. And these facts mean that meters distort all measurements. Sometimes so little, we don't even have to worry about it. Other times a lot, and we have to worry about it. So that's the point of today, figuring out exactly how much and whether or not we need to worry about the meter distorting the measurement. All right, so jot this down if you haven't already. And now I'm going to erase to make room for case 1A over here. So case 1A. So case 1A, the ammeter's effect is negligible. And The reason why that would be the case is that the equivalent resistance of the circuit is large. And what do I mean by large? Well, it means that it's just going to be larger than the resistance of the ammeter itself. So this is the circuit. Let's suppose we've got a battery here, 5 volts, and then the ammeter here, and then over here, a resistor. And I picked some numbers so I, don't need to punch buttons on a calculator. Let's suppose this is 1,000 ohms. So what I mean by a large resistance is it's much greater than this 0.5 ohm resistor of the ammeter. So what I'm going to do is I'm going to analyze what the current will be ideally if this is 0 resistance, and then what it is actually. So ideally, we would just use Ohm's law. I equals V over R, which in our case is 5 volts over, oh no, let me do this on the lower line because I'm going to need room over here. I think I wanted, I guess I wanted 1,000 ohms. Okay, 0. So simple calculation, just voltage over resistance, boom, we got the I ideal. So this says I ideal, the ideal current. What I'm going to do now is calculate what the current is for real. I could have wrote the word actual, but it takes up too much room. So I'm just going to say the real current is, well, we've got 2 resistors here. The ammeter, 0.5 ohms, plus the 1,000 ohms, 5 volts. Now when we're dividing this, instead of dividing 5 by 1,000 like over here, we're dividing by 5 by 1,000.5. It's not going to make much of a difference. In fact, we get oops. And so you see, what's the difference between 0.005 and 0.0049975? Not much. In fact, if you calculated the percent error between, or the percent difference between these two, you would get about 0.05% difference. Or you could say error if you want. So that doesn't make much of a difference in your measurement at all. By having the fact that this ammeter has resistance, putting the ammeter in, okay, I should say it more this way. If I don't have the ammeter, the current coming out of the battery is this. I put the ammeter in and I say, oh, I know what the current is, it's this. No, it's actually now changed to that because of the addition of the ammeter, making a little bit of a difference. All right, so if you didn't get a chance yet, I'll create a pause to allow you to copy this down. All right, let's move on to case 1b. So this means the ammeter doesn't make much of a difference. When does it make a difference? Well, it makes a difference when we start getting smaller and smaller resistances in the circuit. So here's a case where we have the 5 volt battery, 2 ohm resistor. Before the ammeter is put in, we use Ohm's law and we get 2.5 amps coming out of the battery. Then we say, geez, I'd like to measure that and see if that's correct. So we put the ammeter in. Now, instead of 2 ohms of resistance, we've got 2 ohms plus 5 ohms because these are in series. This is just another resistor now. And so when we divide 5 by 2.5, we get 2 amps. And that now is a big difference. It's actually, if you did a percent error calculation, it's 20% different now. By adding the meter, you have distorted the circuit. You've changed the current by 20%. Okay, so your measurement is not what it would be without this. All right, so go ahead and I'm going to go ahead and create a pause, and I'll give you a chance to copy this down. All right, so again, recap with ammeters. If the resistors are large, this becomes negligible. When the resistors get small enough, this now becomes significant addition of ohms to the circuit, and thereby creating a bigger impact. Let's now take a look at how voltmeters change or maybe do not change the circuit. So we move on to case 2A, which will be voltmeter effect is negligible. When is that the case? Well, when the R's are relatively small. And the reason why small is in quotes, because it can still be thousands of ohms, as long as it's much less than the millions of ohms of the voltmeter. And I'll show you how. So let's suppose this is our circuit. Maybe I'll move that over a little bit. Simple series circuit. The battery voltage will be 10 volts this time. And the resistors will be 3,000 ohms and 2,000 ohms. So instead of writing zeros here, I'm going to clutter up my diagram. I'm going to put K for like kilo, like in kilograms, but we're going to have kilo ohms. That means 3,000 ohms. This will mean 2,000 ohms. And what I want to do is measure the voltage of this resistor and see what it is as a measurement. So I put my voltmeter like this in parallel. Now in the ideal case, this is how I'd go about that calculation. So I would first have to calculate the current in the circuit. And I could do that with Ohm's law. I equals V over R, which will be, and I have to use the total volts over the total resistance. And this would be 3,000 ohms plus 5,000 ohms. No, 2,000 ohms. So we're dividing 10 by 5,000, which gives us 0.0020 amps. Okay? Now, in series, this gets a part of the 10 volts. Once we have the total current, what we could do is calculate the voltage here by using Ohm's law again with that total current. And now we could say the delta V measured by that ammeter will be IR, just rearranging Ohm's law. And the current is, as we just determined, 0.0020 amps. And the resistor there is 3,000 ohms. And so when you multiply that, the voltage that we should measure with that ammeter is 6 volts exactly. Oops, let me put the subscript ideal here. But the voltmeter, as I said, distorts this measurement. It will not be 6 volts because this is not an infinite resistor. It's a 10 million ohm resistor. So let's take a look at how much this measurement is distorted by this meter. Okay, so again, maybe I'll just use the word real again. And what I have to realize then is that the circuit is a 10 volt battery as before. This is 3 kilo ohms, 2 kilo ohms, but the voltmeter up here, well, I might be too high here. Yeah, I guess maybe I should lower this a little bit. I'll start up here, 10 mega ohms. Okay, and 3 kilo ohms, 2 kilo ohms, and 10 mega ohms up there. To figure out what the voltage is here to here, from point A to point B, what we have to do is first figure out and treat this as a combination circuit. Figure out the REQ here, figure out the REQ again, and then figure out the current, and then the voltage. So the first step is we realize these are in parallel, so we can find the equivalent resistance of those two by using the reciprocal rule. 1 over 3,000 ohms plus 1 over 10 times 10 to the 6th ohms to the -1 power. Punch that on a calculator, and it comes out to 2,999.1 ohms. 99.1, I think. Yes. 2,999.1 ohms. So this circuit isn't really like this with 3,000. It's 2.999 thousand instead. So we redraw the circuit. This is still 2,000 ohms. But this now acts, because of the addition of the voltmeter, as 2,999.1 ohms. All acted on by our 10 volt battery. Now, we can now finally figure out the current and then the voltage following this similar pattern where we say I equals V over R. In other words, we got 10 volts all over 2,999.1 ohms plus 2,000 ohms. So we calculate that out, and we get slightly more current because we have slightly less resistance. Okay, so that is going to be 0.002000, I think it's 3 zeros. Yes, 4 amps. just a tiny bit more current in this case. And now we can find the delta V from here to here, which is what the voltmeter measures, by using Ohm's law with the I and the R together for V. And so we can get 0.0 times this 2999, and we get the real voltage is 5.9992. Not 6. That voltmeter changed the voltage by, as soon as it truly is 6 volts when the voltmeter is not there. As soon as you touch the voltmeter probes, the voltage drops to 5.9992. Not much of a big deal. In fact, if you calculated a percent error here, you would get 0.012%. So this is 0.012% difference. So there it is, ideal calculation real. Let me create a pause to allow you to catch up if you need it. So again, not much of a difference if the resistances are small. They could still be in the thousands, but they have to be smaller than the millions. The next case we're going to do, the final, is when is the voltmeter not negligible? And the R's will no longer be small. They're going to be comparable to this, somewhere in the millions. When you start dealing with millions of ohms, voltmeter is going to now create a significant difference compared to this situation. So let's move on to the final case here. Case 2B, I think it is. All right, so here's the circuit. We've got the same circuit, 10 volts. But instead of 3,000 ohms and 2,000 ohms, we've got 3 million ohms and 2 million ohms. And we put a voltmeter here to measure what the voltage is of this 3 million ohms. So we're going to find out that it's a portion of 10 volts. It's going to come out to 6 volts again, exactly, if the voltmeter is ideal. So for ideal, we would first calculate the current using Ohm's law. In other words, 10 volts over 3 times 10 to the 6th ohms plus 2 times 10 to the 6th ohms, because these two are in series. So we just simply add to get Req, divide with Ohm's law, and the current here came out to be 2 times 10 to the minus 6th amps. So then, to find that voltage, now that we have the current in the circuit, we could just use Ohm's law again, V equals IR. That current, 2 times 10 to the minus 6 amps, times the resistor there, which is 3 million ohms. Multiply those out and you get delta V ideal equaling 6.0 volts exactly. Okay. you need a moment to catch up, I'll create a pause to allow you to copy this down. Now let's calculate what the voltage measurement will actually be when you touch that voltmeter on there. In order to figure out that, we've got to realize that that voltmeter is actually a resistor, 10 million ohms. Three mega ohms, 2 mega ohms. So to analyze this now, realizing this is actually a resistor, we've got to treat it as a combination circuit where we're solving for the voltage between these 2 points. The way we do that is first to realize the voltmeter and this resistor are in parallel. So right here we're going to start with the parallel resistor rule to find the equivalent resistance of these two. REQ, the reciprocal rule, which is 1 over 3 times 10 to the 6th ohms, plus 1 over 10 times 10 to the 6th ohms to the -1 power. Punch that on the calculator, and what you get is 2.308 times 10 to the 6 ohms. So the way this circuit actually behaves is not like this over here. It behaves like this. We've got a $10-volt battery here. These two act like a 2.308 mega ohm resistor, and this is still a 2 mega ohm resistor. Again, we want to find the voltage of that resistor, so we've got to first figure out the current and then use that current in Ohm's law to figure out the voltage. So let's go ahead and do that. Ohm's law, I equals V over R. What we have is 10 volts, 2.308 plus 2 times 10 to the 6th. So having slightly less or significantly less resistance, we're going to have significantly more current, which in this case is 2.321. Okay, hopefully you could see that. It says 2.321 times 10 to the 6 amps compared to this. Significantly more current. And now the delta V between these 2 points you find with Ohm's law, V equals IR. That current, because it's a series circuit, minus 6, sorry about that, 10 to the -6 amps. And then the resistance between those 2 points is this. Multiply those together, and you get a voltage of 5.36 volts. Now, again, I want to emphasize, actually, you know what I'll do? I'll create a pause first to allow you to copy this down, then I'll interpret. So again, this is not a measurement error. It's a measurement distortion. It actually changes the current, the voltage. Before you touch the voltmeter here, the voltage truly is 6 volts from there to there. As soon as you put the voltmeter on, the voltage truly is this. The meter has changed the circuit, changed the current, changed the voltage between these 2 points because it's a comparable resistance to what you're touching. Close, all right? So that is significant, unlike the previous example, because if you do a percent error, you get about 10% difference. Okay. So that's the topic for today. A reminder, meters always distort measurements of current and voltage. Sometimes those distortions are so small we don't even have to worry about it. Sometimes they're quite big. You distort the circuit, so when you measure it, the circuit's values you're getting are truly different by 10, 20%, even higher in some cases. The key difference is that with an ammeter, which has hopefully a zero resistance, but really more like a 0.5 ohm resistance, if the resistors are all large compared to that, thousands of ohms or maybe even hundreds of ohms, thousands, millions, then the ammeter doesn't distort much. But when the resistors get small in the circuit, down to, in the single digits of ohms, that 0.5 ohm now makes a significant impact on the REQ, thereby reducing the current in the circuit, the very act of inserting that ammeter, to a large degree to make a significant error. So small resistances, lots of error with an ammeter. With voltmeters, it's the opposite. If the resistors are all small, then the voltage distortion is small, insignificant, even thousands of ohms. The voltmeter doesn't change the readings by much, or the values by much, I should say. But when you start dealing with circuits that are made of millions of ohms, lots of resistance comparable to the voltmeter, then the voltmeter changes the circuit significantly in the circuit. In the AP, you have to be able to quantify the amount these changes occur, which basically means you do exactly what I did. In the beginning, you pretend the ammeter has either zero resistance, analyze, or 0.5, analyze, and you look at the difference, 0.5 ohms. So you just solved the circuit problem twice. With the voltmeter, you do the same thing. First, you pretend the voltage truly is infinite and you solve. Then you treat the voltmeter as a 10 million ohm resistor or whatever they tell you it is in the circuit, and you reanalyze the circuit and get the new value. And then you compare to see how much of an error that device introduced into your analysis. So that's voltmeter and ammeter distortions. I hope you enjoyed the video. I'll see you in the next physics video.